Hello, welcome to Numeristical. Today we're going to be taking a deep dive into the AUC, also known as the area under the curve or the C-statistic. And to give you a brief outline of what we're going to discuss, we're going to start by giving an introduction as to why the AUC is relevant in machine learning. Next, we'll give the graphical definition of the AUC as literally the area under the ROC curve, and we're going to walk through an example of actually drawing out the ROC curve and computing the area underneath it. Then next we'll demonstrate an equivalence to another way of thinking about the AUC number and interpreting it in practical situations, which is that actually the AUC number can be thought of what's the probability that you correctly order a randomly chosen pair of items from different classes. And we'll demonstrate that and make that explicit. And then finally we'll talk about how AUC can be misused in practice. Often people give slightly incorrect interpretations to AUC or make incorrect judgments about when it's appropriate to compare AUCs in different situations. And we'll discuss and walk through some of that. So it's a lot to cover. So for this video, we're just going to start with the introduction and talk about why AUC is relevant for machine learning. So what is the AUC? Well, as you probably know, AUC stands for area under the curve. Now, of course, this begs the question, what curve are we talking about? We're talking about something called the ROC curve. And sometimes to make this very explicit, you'll see it referred to as the AUROC. And the ROC itself is a very cumbersome acronym. It's called the Receiver Operating Characteristic. And that terminology dates back to its original use, which was in radar systems in the military. But before we get drowned in jargon and acronyms, let's talk about why the AUC is relevant for machine learning. So, the first thing to have straight in your head is that AUC is a performance metric for binary classification models. So, in binary classification, of course, the goal is to build a model which can distinguish between items from two different classes. So, examples of this might be, say, fraud detection. We're trying to distinguish between fraudulent and legitimate transactions. Another example might be loan default prediction. We're trying to distinguish between people who will pay back their loan and people who will not pay back their loan. And then the second thing about AUC is what makes it really compelling and so widely used is that it measures the quality of a ranking prediction. So it's used in the context where you have a model and a test set, and your model is going to, one way or another, give you a ranking of all the cases in the test set and saying, at the top we have the ones that are most likely to be a 1, and at the bottom of this list we have the ones that are most likely to be a 0. And AUC is going to say how good that ranking is as a ranking. Now, you might say, well, there are other classification metrics that do that as well, right? What about things like accuracy, precision, recall, sensitivity? Don't those all kind of do the same thing? And the answer is no, actually. Those metrics measure the quality of hard predictions. So to use a metric like that, you have to make a hard call on each case and say, I think this is a 1, I think this is a 0, and so forth for every case. And then you could compute an accuracy number or a precision number or a sensitivity number. But they do not measure the quality of the ranking overall. You have to convert that ranking into a hard prediction, which is usually done by choosing a threshold. And we're going to walk through an example of that to make this a little more clear. So the example I want to talk about is fraud detection. So let's imagine we've built a fraud detection model. And what this model does is you give it the details of some financial transaction, and it spits out a score. And the score is just a number. And when that number is bigger, it means that the model thinks this is more likely to be fraud. And when the number is smaller, it thinks it's less likely to be fraud. And that's really all you know about the number. So let's say we evaluate this now on a test set of, say, 15 cases. And these are the 15 numbers we get. So the first thing I want to do is sort these numbers so that the biggest numbers are on top and the smallest numbers are on the bottom. And again, bigger numbers mean it's more risky, more likely to be fraud. And then we're going to evaluate, or we're going to see what the true answers actually were. So we get this list. We see that there's 5 ones, so there's 5 fraud cases. The ones are the fraud cases, the zeros are the legitimate transactions. And the first thing I want you to try to do is just try to judge how good this model is doing subjectively without doing anything else. And you might notice a couple things. The first thing you might notice is, well, it's not perfect. If it were perfect, the ones would all be on the top and the zeros would all be on the bottom. There'd be a nice clear separation. So we don't have that. At the same time, it is doing something reasonable, right? The top 2 most risky transactions both ended up being fraud, and 3 out of the top 4 also ended up being fraud. The 4th and 5th cases maybe didn't do so well on. The 4th case was kind of in the middle of the pack, and the 5th case was near the bottom. So it didn't do as well on those cases, but it's doing something, right? It doesn't look like those ones and zeros are kind of randomly distributed in the ordering. Now, if I were to try to use a measure like accuracy or sensitivity or specificity to evaluate this model, I would have to choose a threshold because, as I said before, those metrics measure the quality of a hard prediction. So we're going to discuss 2 metrics in this class. We're going to discuss sensitivity and specificity, and this is because these are the 2 metrics that will ultimately be very relevant for computing the AUC. Now, let's look at these in detail. The sensitivity asks us to compute what fraction of the fraud cases did we correctly declare as fraud. So we're going to choose a threshold, declare everything above that threshold to be fraud, declare everything below that threshold to be legitimate, and the sensitivity says, what percentage of the fraud cases did you correctly label fraud? The specificity asks, what percentage of the legitimate transactions did you correctly label as legitimate? So let's go through a specific example. Let's say we set the threshold at 50, and we draw a line at 50. So everything above that line we're going to declare as fraud. Everything below that line we're going to declare as legitimate. So in this case, our sensitivity would be 3 out of 5, or 0.6, and our specificity would be 7 out of 10, or 0.7. And that's because 3 out of the 5 fraud cases are above the line, and 7 out of the 10 legitimate cases are below the line. Now, suppose we changed our threshold. We decided to use 55 as the threshold, move that bar up a little bit. Our sensitivity stays the same, but our specificity now goes up to 90%, or 9 out of 10. And you can see we've kind of chosen a more favorable place to choose that threshold for this test set. And the point I'm trying to make here is that it's the same model, it's the same set of scores that we gave to everything, it's the same ranking, but we'll get different sensitivity and specificity scores depending on what threshold we choose. And that's kind of a weakness of those measures. If we really want to just evaluate how good was the model at ranking these cases, it would depend on our choice of threshold. And we wouldn't know if it's doing poorly. Is it doing poorly because we chose a bad threshold, or is it doing poorly because it's just a poor model? A second thing I want to point out is that the denominators of these metrics for a particular test set are going to be constant. So since there's 5 fraud cases, my sensitivity will always be some integer over 5, and my specificity will always be some integer over 10 because there's 10 legitimate transactions. So this will come in relevant when we start drawing the AUC curve. We're going to see that the sensitivity in this case is always going to move in steps of 0.2, and the specificity is always going to move in steps of 0.1. Now finally, what I want to motivate for AUC, the problem it's really good at solving, is that we want to evaluate this model and its ranking without choosing any particular threshold, and also without making any judgments as to how we want to trade off false positives and false negatives. If we knew exactly where we wanted to operate in terms of our tolerance for false positives and false negatives, it might be reasonable to say, okay, I'm going to examine certain thresholds in certain ranges. But if we're just developing a model, we're still not really sure how we're going to use it. We just want to say, I want something that works pretty well across all possible thresholds in all ranges of the curve, in all ranges of trading off sensitivity and specificity. So what we really want is something that doesn't even depend on the numerical scores that generated the ranking. So that's a really interesting thing about AUC is it really just depends on what's the order of ones and zeros once we make this ordered list from most risky to least risky. It just depends on that string of ones and zeros. It doesn't even depend on what the numbers were behind it. So for example, suppose I had two different models, and with our first model, which is the one on the left, and the second model is the one on the right. If we had these two different performances of ranking, it's not really obvious how to say which one of these models is better than the other, right? Because if I choose a threshold here, for example, the model on the right is better. It got 4 out of the 5 fraud cases on the right, and the other one only got 3. But if I bring the threshold down here, now the model on the left is better. It caught all 5 of the fraud cases, whereas the one on the right only caught 4. So what AUC is trying to solve is to give a metric that kind of averages across all thresholds. It says, what's the average performance of these models across all thresholds? And that's why it's very useful, and that's why it's so really dominant in these situations in terms of its usage. Okay, well, hopefully this piqued your interest. In the next video, we're going to discuss the graphical definition of AUC, and we're really going to go through and draw out this curve and show some really interesting aspects of it. So I hope you'll join me for that. If you enjoyed this, please like the video and subscribe to the channel. It really helps me in order to be able to produce more content like this. And thanks for watching, and have a great day.